All right. Well, welcome back, folks. And I want to go ahead and pick up where we left off with yesterday, and that is we were talking about how we can obtain masses for a given substance in a chemical reaction. So we were talking about chemical reactions. We were dealing with balanced equations. We were talking about how we can use balanced equations to obtain information about the reactants, the amounts, the quantities of reactants and products within that chemical reaction itself, and we can use then the coefficients in order to obtain information about number of particles, number of atoms, moles. But we said then with all those, when we identify the quantities there, we really can't use those quantities in order to actually carry out the reaction. And so we have to convert it to masses. And so we did. We went through quite a few examples yesterday of a moles to mass conversion, which is what we did back in chapter 10. So please make sure you take a look at that. And so from that conversion, we were able to obtain masses. Okay? And so we saw then, and when we compared the masses of reactants that we started out with to the masses of the products that we form and we end up with, the masses are the same. So we have this conservation, meaning then that we start out with a certain mass, a total mass, we have to end up with a total mass that's exactly the same. The substances will not be the same, obviously, because there's a change that has to occur, but the masses have to be the same. Okay, so that's the fundamental law of physics. It's the first law of thermodynamics, and so you for some of you you'll learn that as you move on, but that has to happen. So we saw then that atoms have to be conserved. That means the number and type of atoms that you start out with has to be exactly the same as the number and type of atoms that you end up with. And so atoms are conserved, and so are masses. Okay, and so make sure you keep that in mind as you move forward. Okay, and we'll practice this some more. And so when we do stoichiometry, when we start our lesson on stoichiometry today, where we're doing mass to mass conversions, the conservation of mass will still hold, and you have to be aware of that. That is always something that's in the background that you have to be aware of. Okay. All right. So with that said, then let's go ahead and let's practice this here. Okay, and let's go ahead and get this done. Okay. You're given this problem here, and I want to work this out with you. You're given this equation. It describes the reaction between dihydrogen sulfide with oxygen to form sulfur dioxide and water in a 2 to 3 to 2 to 2 ratio. Okay, we want to find then the representative particles. We want to use this to. We're going to use this equation, this problem to practice everything we've done so far. We'll interpret it in terms of moles. Okay, so we'll identify the quantities of moles, and then we're going to identify the masses of reactants and products as well. Okay, so let's go ahead then. Let's work this one out together. Okay, and then I'll give you a chance to work it out on your own. Okay, let's go ahead and let's identify particles first. Okay, so we don't have to worry about atoms. So on the particulate level, okay, we're saying then that basically what we're saying is the molecules. Okay, so we are identifying the number of molecules involved. Sorry, in the reaction itself. All right, so then we start out with 2 molecules of H2S, and to that we react 3 molecules of O2. Those are reactants. Okay, products then will form 2 molecules of sulfur dioxide and 2 molecules of water. Okay, so we're just identifying the total particle here, so we're not identifying the atoms. This is what we refer to as molecules, but this essentially then is the representative particle. We can apply this here also to ionic compounds, which are technically not molecules, but we remember when I pointed this out to you in the book, and you'll see this elsewhere as well, the term molecule is going to be used fairly generically to just refer to these representative particles. Okay? So therefore, we start out then with 5 total particles, okay? And we end up with 4 total particles. And if you notice, the number of particles are not conserved, meaning they are not the same. That means they are not equal on both sides. You start out with 5, you end up with 4, and that's fine because particles do not have to be conserved. Okay? All right, let's go ahead and let's interpret it on the level of the moles. Okay, moles of each one of these components. Okay, so we have then 2 moles of H2S to start out with, 3 moles of oxygen to start out with, Okay, and if we mix that quantity together and the reaction runs correctly, we end up with 2 moles of sulfur dioxide and 3 moles of water. I'm sorry, two moles of water. Sorry. Okay. We end up with 2 moles of water. Again, you'll notice that we don't conserve moles here. Moles are not conserved, meaning that they're not the same on both sides, because we end up with 5 moles total. We start out with 5 moles total on the left. We have then 4 moles, total moles on the right. And again, they're not the same. Thus, we don't see conservation occurring at that level either. Okay. All right, so let's go ahead then and let's do masses. Okay, so let's go ahead. This is where we have to calculate. Okay. All right, so for the first two, we didn't have to calculate. We can just take it directly from the balanced equation, but we do have to calculate here. So with that said, then let's go ahead and do the calculation. So if we start out with 2 moles, okay, of H2S, we're going to do the conversion here to grams of H2S. Molar mass here, we're going to plug in then. It's going to be 68.2 grams of H2S over 1 mole of H2S. And let me just check to make sure my math is correct here. I don't have you guys around to keep me honest and point out my mistakes. So we got 32, I'm sorry, 34.1. Sorry, that would be the total moles. So that's why I said it didn't look right to me here. So this is going to be 34.1. That looks better. Okay, so 32 plus 2 is 34.1, and then our total mass is 68.2. Okay, 3 moles of oxygen, O2. You get the grams of O2. This one's going to be 32 grams per 1 mole of oxygen, which is going to give us your 96 grams of oxygen. Doing the same thing with the other two, with the 2 products. Okay, we have 2 moles of sulfur dioxide. We're going to convert that into grams of sulfur dioxide. Okay, here it's going to be 64.1 grams for every 1 mole sulfur dioxide. We'll end up here with 128.2 grams, and then finally 2 moles of water, H2O, grams of water. This will be 18 grams H2O for every 1 mole H2O. And we end up here with 36 grams of water. Okay. All right, so these are the amounts that we start out with. Okay, this is the mass that we start out with. We add that up, we get 164.2 grams total reactants to start out with. We add these two together, we end up with 164.2 grams total as well. And that makes sense then, because remember, mass is conserved. Okay. All right, so make sure you practice that, folks, and get that done. What I would like you to do then, and let's go ahead and get this done. And I want you to go ahead and let's do number 15 in your problem set. Use the problem that we just did here. Take about a couple of minutes to work out this problem here. Interpret this equation, okay, and interpret this particular reaction. Here they describe the reaction to you, so be careful on this one. They don't actually give you the equation itself. They describe the reaction to you. You have to come up with the correct balanced equation, and then go ahead and interpret the balanced equation in terms of number of molecules. So let's go ahead and do this. Okay, so make sure you interpret the equation in terms of number of molecules, okay, moles, and volume here. Okay, a volume here. And so go ahead and get that done. Take about 3 minutes, and then write down your answer on your paper. Come on back, and then we'll compare answers. Okay. All right, so go ahead and get this done. All right, let's go ahead then, and let's take a look at what we have. Okay. We have then a description. Okay, so we're told then that we want to find the formation of water. If we are forming water will be a product. Okay. Formation of water from its elements. This is going to be a combination reaction. Okay, hydrogen plus oxygen as a gas to form here water vapor as a gas, and we're saying that the reaction is run at STP, and that's going to be important in just a moment. All right, so there is the skeleton equation. This is all the stuff we learned back in chapter 11. Okay, so the balance equation then is going to be 2, 1, 2. That is the balance equation that we will have there. Okay, let's take this then and let's go ahead and answer the questions about molecules first. So let's go ahead at the molecular level. Okay, molecules. Let's count molecules. Okay, so therefore we start out with 2 molecules of hydrogen and 1 molecule of oxygen. Remember, the no coefficient here represents, if there's no number here, that represents 1. And we end up with 2 molecules of water. Okay, so we have then 3 total molecules. Sorry, this is giving us problems again. And we end up with 2 total molecules. And if you notice here, we don't have conservation because this on the molecular level. Okay. All right, let's go ahead and do moles. Let's go ahead and count moles. We have then 2 moles of hydrogen to start out with. We're reacting out with 1 mole of oxygen to start out with. Okay. And then we end up with 2 moles of water. Okay, so total moles, then we have 3 total moles to start out with. We only have 2 total moles to end up with. And so if you notice, then the number of moles do not equal, the no conservation there as well. Okay. All right. So here they're not asking us about masses, but I'll do that for you in just a moment. But let's go ahead and do volume first. Okay? So they ask us about volume. We cannot obtain volume directly from the balance equation. We have to do the conversion, but that conversion is simple because since these are all gases at STP, we can use the molar volume, which gives us the volume in liters of a gas of 1 mole of the volume of 1 mole of a gas, okay, at STP. So we can use this conversion factor to get this done, which ends up being fairly simple. So let's go ahead and start out here. We have 2 moles of hydrogen. We get that from this information here. We can find then the volume of hydrogen involved in this reaction. That means then we're going to multiply by the molar volume, which is 22.4 liters. In this case, then it's of hydrogen over 1 mole of hydrogen, and that gives us then 44.8 liters. Okay, doing the same thing with oxygen, 1 mole of oxygen. You're going to find the volume of oxygen, 22.4 liters of O2, 1 mole. And if you notice here, the identity of the gas will change, but the volume that is occupied by that 1 mole will always be the same. And that was Avogadro's hypothesis that we talked about back in an earlier chapter. Okay? All right, so this will give us then 22.4 liters of oxygen back in chapter 10. Okay. All right, so finally with water then, 2 moles of water. This time though, we want to find the volume, not the mass of H2O. Okay, and so again, we're going to use the same number. The only thing that changes then is the identity. But again, remember the identity does not affect the volume that is occupied by 1 mole of the gas itself. So here we're talking about water vapors. Okay, so we plug that in, that's going to be 44.8 liters as well. Okay, and so if you notice then you total it up here. Okay, the total here, let's go ahead and do that. Let's be 67.2 liters. 67.2 liters. Obviously that's not equal to 44.8 liters. So they're not equal because mass is volume is not meant to be conserved. We don't expect that to happen. Okay? So hopefully you have that. Make sure you write this down on your paper as well. Okay, to make sure you have that to compare to what you did, and to make sure that you did everything correctly. Okay, let's go ahead then. I want to do one extra thing here, and I want to ask you then. Oh, sorry. Okay, I want to ask you then. Let's do masses. Okay, so let me just quickly write this out again. Sorry, I erased that. Erased too much. Okay, so it's going to be 2, 1, 2 gas. Okay, let's find volumes here. Let's find volumes here, right? Okay, I'm sorry, masses here. So let's go ahead and calculate for masses. We saw then that the number of particles wasn't conserved, the molecules was not conserved. We saw that moles were not the same on both sides. We saw that the volume's not the same on both sides, but based upon our discussion in class this morning, we should expect the masses to be the same. Okay, so let's go ahead and let's calculate for masses. Okay, so we have then 2 moles of hydrogen. We want to find now the mass of hydrogen, and we're going to use the molar mass here of 2 grams of hydrogen for every 1 mole of hydrogen. So that would be then 4 grams of hydrogen. Let's do the same thing with oxygen. We have 1 mole of oxygen. We want to find the grams of oxygen. That's going to be here 32 grams of O2 over 1 mole. O2, that'll be 32 grams of oxygen here. And then finally 2 moles of water. Okay. We want to find the mass of water equivalent to it. Water then is going to be 18 grams of water for every 1 mole of water, and that'll give us 36 grams of water. And so if we add up the masses of the reactants here, we end up with 36 grams total. Okay, and obviously the mass of the product then is 36 grams total. And if you notice here, the mass is equivalent. So mass is conserved in this case then, and that's what we expect to happen. Okay. All right. Very good, folks. What I'd like you to do then, and let's do another practice problem here. Okay. Let's do number 16 in your problem. So take about a minute and a half, maybe 2 minutes to work out this problem here, and then we'll work this problem out together, and then we will finish up for the day. And what we'll do tomorrow is then we'll start then with the calculation involving stoichiometry. Okay, so take about a couple of minutes, compare the masses of the reactant to the product with this particular reaction. Okay, so go ahead and get that done, and then we'll go over together. Okay, take about 2 minutes. Okay, let's go over this problem here together, folks. Let's find out how you got this done. First of all, always check to make sure that the equation is balanced, folks. And you're going to notice here that this equation is not balanced. It's not a balanced equation, so you got to go ahead and you got to balance it first. Okay, so if you could not balance it, please make sure you combine CME. Okay, this is a bit more challenging to balance, but like I said, I think you should be able to do it. So it's going to the balance equation is be 4, 6, 5, 6. Okay, so those are the coefficients that we will use to balance the equation. So again, this equation may be a little bit more challenging. Possibly, maybe most of you got this, but if you did not get this, combine CME and get help with it. But that's the balance equation. Those are the coefficients that we need to balance the equation. All right, and so now they're asking us to find the masses of the reactants in the product. But to do so, you have to recognize then that we need moles to start out with. And so that means then these coefficients, remember, the coefficients gives us the amount of moles directly. So we have then 4 moles of ammonia to start out with. And we want to find the mass. So make sure you're okay with where this number comes from. It comes from directly from the balance equation. That's why we need it. So with this amount now, we can go ahead and solve for the mass of ammonia, okay, to do that. So therefore, to do that, then we're going to plug in the molar mass for ammonia, which is going to be 17. 14 plus 3 is going to be 17 grams of NH3 for every 1 mole of NH3. Okay, and so you plug that in, you're going to get your answer as being 68 grams of ammonia. Okay, all right, let's do the same thing for nitrogen monoxide. Okay, so the coefficient here tells us that we start out with 6 moles of NO. We want to solve for the grams of NO, nitrogen monoxide. The molar mass of nitrogen monoxide is going to be 30. Okay, so 16 plus 14, yes, so 30 grams of NO for every 1 mole of NO. And then you plug that in, then you get 180 grams there. Okay. All right, let's do the same thing for so those are the masses of the reactants. So these are the reactants here. Sorry, let me go ahead and erase that real quick. These are the reactants here. Let me go ahead and finish up. Okay, so these are the masses for the reactants. Okay, let's go ahead and do the same thing for the products. Okay, so we have then 5 moles of nitrogen, dinitrogen. Okay, that's the elemental form of nitrogen. We want to find the mass of nitrogen. Using the molar mass of nitrogen, it's going to be 28 grams for every 1 mole of nitrogen. And then we'll end up here with 140 grams, okay? And then finally for water then, we have 6 moles of water. And again, we expect to form 6 moles of water. If we take these amounts of ammonia and nitrogen monoxide and react them together, we're gonna form 5 moles of nitrogen and 6 moles of water. And so let's go ahead and find out then the mass that's equivalent to this. Okay, so we have then grams of water, and this is gonna be 18 molar mass is going to be 18 grams for every 1 mole of water. We plug that in, then we'll get 108 grams here. So this represents then the products. So those are the masses of all the products. So real quick here, let's add these up and add this up here. Okay, we end up here with 248 grams total. This is total mass of the reactants. And if you notice here, we'll end up with 248 grams total mass for the products. The masses have to be equal. And so the lesson today then, and make sure you keep this in mind, what I want you to be able to take away from the lesson today then is that when you run a chemical reaction, or any process actually, let's generalize this a little bit further, okay? Any process that occurs in nature, in this universe, any process that occurs, the amount of mass, the matter that you start out with has to be the same as what you end up with. What you start out with, what you end up with has to be exactly the same. That's the first law of thermodynamics. Now, with that said, does that always happen? Actually, no, that never happens. And we'll learn why towards the end of this chapter. But the expectation is, and what the law tells us, is that the amount of matter that you start out with and the amount of matter that you end up with has to be exactly the same. Why in practice it's not the same? That's something we'll talk about at the end of this chapter. Okay. All right, folks. So very good. I'm going to go ahead and I'm going to assign the next homework assignment, set B for chapter 12. Please make sure you get that done for tomorrow. If you have any questions on it, come by and see me, and then we'll go ahead and work that out together. Okay, so get the homework done for tonight, and then we'll continue the discussion tomorrow by talking about mole ratios, and then we'll start our first stoichiometric calculation tomorrow. Okay, all right, folks, very good. Have a good day, and I'll see you tomorrow.